Hi, everybody. Thanks for the opportunity to have a chat with you. Um, Anybody attended the SciC Geotechnical lecture? You're about to get some regurgitation, so apologies for that. I don't know how many people were at that. Uh, but when Wesley approached me, I thought this might be a reasonable topic to look at. The the case study aspect of it is probably a bit random because this is such a massive topic. The decisions that us geotechnical engineers take are heavily influenced by geological setting, and it's a great fear of mine that a lot of geotechnical engineers today don't give this enough priority, and that's where this all came from. So we're going to be looking at the geological setting. I'm going to delve into a case study on sedimentary rocks, but there's a massive amount of influence that geological setting has on geotechnics. Discontinuities are one thing, the strength and parameters are another. Um, in the specifically something like the tailings field, the soils derived from host geology is a very critical aspect. So, but I'm going to have a quick look at tectonic history and the basic formation of sedimentary rocks, purely because it fits some of the more interesting outcomes of my case study. Um, so where do I start? I start there, and I wish all of the engineers I worked with started there as well. Um, there's an incredible amount of information that has been gathered in the past, and a whole array of geological maps that are available to all of us. A lot of people ignore them to their peril. There's also other information. This book got a little bit of a show yesterday. There are 4 volumes to this. Um, they are essentially set in the various geological time periods. I have these books digitally, and I will be doing a check on whether there's any copyright infringement pertaining to me giving them to you. If there isn't, I'll probably work through Wesley to get them to you, but we've got these books digitally. They're extremely useful. I'll try and reference why through the case study that I look at. We spoke yesterday about a narrative about building credibility in the geophysics world. These books came from a PhD that was done. It then attracted a bit of interest from the Geotechnical Division of SciC and the Association of Engineering Geologists, who funded getting the book together. But there are a couple of names there. If anyone works in the geotechnical world, they'll understand the significance of some of those names. In my view, in the geophysics world, some of those names sit in this room. So it would be a massive undertaking, but it would be a fantastic achievement to put something like this together to improve the status of geophysics in the world that we live in. I just thought I'd pop that in. Let's get to the sedimentary rocks and the case study. So sedimentary rocks essentially formed from particles accumulating or deposited in low-lying areas that are compressed back into rock. So sedimentary rock is by nature of its formation variable. Um, Different flooding events have resulted in the different layers that you see there. Some of the stuff is fine grained, some of it is coarse grained, and then you bring in all of the movements that have happened and the jointing, etc. So sedimentary rock is an interesting one. It's plagued with variability, and I'll show you how that transpired in my case study. So just a quick very high overview of what happened in South Africa. So when the continents broke up, there was an extension, then a compression, which resulted in the Cape Fold belt, the Cape Fold Mountains in South Africa, and that's where the case study site is located. So we're essentially looking at the Taspent nuclear site, which is near St. Francis. And there you can see the Cape Fold system. And this is all, of course, in a sedimentary rock environment. This is the Table Mountain Group sandstones. Once again, the trusted geological map. This is a bit of a cheat because not every site has its own geological map. This is a geological map that was developed, I think, purely because of the importance of nuclear and the risk of getting stuff wrong. But you can see that I'll show you the cross section now, but the site is roughly over there. This is sea, and that's land. It's better to look at a cross section. So there's the site over there. That's the sea, that grey bit over there. And you can see that this is, in terms of the folding, that was the original fold that has been weathered off, and weathered and eroded off. So you've got a sequence of these sedimentary layers dipping into the sea in relation to the site. The site is over there, and it's the Table Mountain Group rocks. Sorry, it's not very clear, but one of the things to notice is those little orange things over there are actually dunes, and in the scale of what we're looking at here, they're rather significant. There's a hell of a lot of overburden on the site. So what happened on this project was that it's been a nuclear site for some time, so there's been a lot of work done in the past. The cross section we looked at was through there. So the strata are dipping into the sea, and there's essentially the Skirverberg. We picked up a transition zone, the Gaudini, the Cederberg, and the peninsula. Peninsula is same as Table Mountain. But I wanted to show you what transpired from an understanding geological perspective. When I looked at the Brink books before we even put a drill rig on the site, there was a plethora of information that was contained in those books. The books are essentially an introduction with a whole bunch of case studies. And if you read it, you take the time to read it, you can actually find out a whole bunch of stuff. So before I put a contractor on site, I was able to, in the drilling specifications and the like, point out, guys, you're going to have the rock is hell of a hard. There's going to be wear and tear on your equipment, factor it in, all of those types of things. There's a massive amount of information in there, and it is pointed out that in the sedimentary environment, it's variable. So there's a lot of other stuff that was not related to my geotechnical investigation, but there's valuable stuff there that can be found in that book, in that series of books. So historically, the Atomic Energy Commission drilled a whole bunch of holes because nuclear requires cooling water. The emphasis was putting it close to the coast. But as SRK got involved, we did a second phase of drilling, and then a third. The reason that we're starting to move inland here was because trade-off studies showed that corrosion on nuclear equipment is a big factor, so you want to be a little bit away from the sea, and that's why we're moving away from the sea here. So there were a couple of phases of drilling, and then we did a shear wave velocity profiling for the earthquake risk guys, so that they could sharpen up on their impedance calculations. But what I'm showing here is there was a little bit of geophysics done at the time by the Council for Geoscience, but we were ahead of them, so it wasn't all available to us. We did some probing in the soils where we tried to pick up a shear wave velocity profile in the soils, etc. But this, I can't tell you what this cost. I'm not allowed to, I don't think, but it would it would surprise you. A huge amount of money was spent here in developing an understanding of the site. Obviously, it's a nuclear site. We need to know what's going on. We factored in the hydrogeological work, which wasn't exactly geotechnically orientated drilling. It was mud rotary and the like, so we didn't get great logs and that, but we got some good information in terms of groundwater. But where I wanted to go to was the outcome. So the Brink books had already said that this stuff is more this and that is more competent than these sedimentary units, which we knew. But here's the outcome. So if you look at just uniaxial compressive strength, simple testing of the rock, you can see that this is a distribution in the peninsula and in the Skurveberg. Skurveberg, Lindsay is the unit that we're doing Klein Willem in, the really hard stuff. But you can see that the Gardenia and the Cederberg, much less competent. Jeez, Megan is ruthless with this timing thing. Yeah, here's Poisson's ratio in those different units. You can see the difference. I'm going to have to rush. Young's modulus, similar. You can see that what the Brink books were telling us was very much borne out in the actual information. Once again, I can't tell you how much money we spent on laboratory testing, but it was a massive sample and a huge amount of information gathered. So the outcomes, the shape of things. I put this particular cross-section in here on purpose. You can see there's, so let's go here. That was what Brink said was less competent, and the more competent stuff was in either side. But one of the big outcomes of this study was that the wave cut platform that was developed on the site is essentially here, got filled up by cobbles, and this became probably the most significant outcome of the study. So it wasn't. If you look at the groundwater contours, have a look at the shape of these contours and how, when this is the less competent zone and the cobbles are all in here, about 50 meters down, there's about 50 meters of overburden sand here. But look how the water is getting sucked out of here. And look at the shape of the bay, how that was actually eroded out there, because this is less competent than everywhere else. But the nuclear power station will need to be founded on rock from a seismic hazard mitigation, seismic risk mitigation perspective, which means we have to get through a lot of overburden. We have to dewater that portion, but there's a massive cobble bed lying down there. So how are you going to put in some sort of cut-off system, et cetera, et cetera? It's an extremely complicated geotechnical challenge. What happened on this site was that that bedrock profile and the influence on groundwater and what the groundwater and what the dewatering would look like and the environmental impacts of the dewatering, etc., is a big thing. So what I'd like to point out is that I don't think in my career I'll ever be able to spend the money on drilling that I did on this site ever again anyway. In fact, I would be lucky to get 10% of that money on any other site, be it a tailings dam or whatever you want to imagine. And that's where I see the integration between geophysics and the intrusive stuff that we're used to doing coming out, because, oopsie, sorry, I'm trying to go back. Oh, how do I go back? I can't. In any case, the shape of that depression could have been found out through geophysical techniques, numerous of them, and probably at a much lower cost. Right, I don't have any more time. I was going to show you some other shapes of things, but I'm out of time. Any questions?
This is why I'm not in charge of time.
Yeah, I'll show you the shape of things quickly in another context. So this is igneous rock. The way it forms is very influential on what it looks like and its shape. And that sort of shape that you see there manifests underground as well. Specifically intrusive igneous rocks always have this sort of doming structure. And in the Bushveld complex tailings dams that a lot of us work on, we have this igneous rock setting as a foundation. And you often see these straight line things in stability assessments. These are cross sections for stability assessments. When I see straight lines like that, I just know it's absolute bogus. This is an igneous rock setting. We simply don't have that. And this is where geophysics really could help us, because if we could find out the shape of things, and this is an example of some ERT that was done on one of the tailings dam sites that I work on. You can see the shape of things. That's an interpretation of where the hard rock contact is. I don't see any straight lines there, because that's what igneous rock looks like. The impact of this, if we as tailings engineers have a credible failure mode that goes through the foundation, you cannot believe the ramifications that has on environmental considerations, emergency planning, liability, insurance, etc., etc. So we could, if we depict the foundation, for example, in igneous rock with straight lines, and we have a credible failure mode that pops out like that, it has massive ramifications. If we could find out what that looks like, sorry, I can't go back here. If we could find out what that profile looks like, what the foundation, what the founding profile looks like under our tailings dams through geophysical investigations, it is of great benefit to us. Now, any questions?
Any questions while hands are going up all over the room? I was just looking, there is actually a research seismic refraction line going north from St. Francis Bay upwards. If it would help at all, I can send you the paper looking at the different rocks. Anyone else?
I could potentially share the seismic hazard assessment that was done there, because it is in the EIA domain. So it's a very interesting study done by Julian Bommer from Imperial College with.
I'll actually cover that in my talk.
Okay.
Don't steal the line.
We've got it.
Oh, good. Anyone else?